mean GPA of night students is larger than 2.4 at the 0.01 significance level. Then we're going to choose the null and alternative hypotheses. We're going to determine if the test is left-tailed, two-tailed, or right-tailed. And based on the sample data, we'll calculate a test statistic and then find the corresponding probability area value, and then decide if we should reject the null hypothesis or not. So let's begin by wording the claim. So we're going to say the claim in symbols. Test the claim that the mean, so we're going to use the mu symbol, that the mean GPA of night students is larger than 2.4, so we're going to use the greater than symbol. And it says at the 0.01 significance level, so we'll just put that off to the side there. We can use it when we're ready. Okay, now let's get back to the hypotheses. So now that we have our claim in symbols, we're going to determine if the claim falls under the null hypothesis or if it's going to be the alternative hypothesis, H sub A or H sub 1, either way. And now we know that the null hypothesis always has equality, and our claim does not have equality. So that means that the claim is not in the null hypothesis, and therefore it is the alternative hypothesis. And this is a right-tailed test. All right, now that means that this is right-tailed, and we're going to use mu is greater than 2.4. Okay, so we have that so far. Then we're going to focus now on the sample information. So let's begin first, though, by making a sketch. Okay. Now, all of our sketches are going to be the normal distribution, or the t-distribution. Both are bell curved and have mean of 0. So when we're doing a claim about a mean, we need to know if this should be a z-test or a t-test. Now, how we're going to know is whether sigma is known or if the sample standard deviation S is known. Remember, sigma, the Greek letter symbol, is your population standard deviation, and S is your sample standard deviation. So it matters which one we have because that will determine what type of test this is. Okay, Z-tests are always, for claims about proportions, are always going to be Z-tests. And if we're doing a claim about a mean with sigma known, the population standard deviation known, then it's a Z-test. But if it's a claim about a mean with S given instead of sigma, then it's a t-test. We can also see that here in these different formula sheets, or the formula sheet with these different options here. Notice that if we're doing a mean with sigma known, it's going to be a Z. If it's a mean with sigma unknown, it's going to be T. And if it's for a proportion, it's going to be Z. And if it's paired data, it's also going to be T. So you can really use this form to help you know which sampling distribution you should be using. So for this one, we've already determined that it is a claim about a mean. So it's going to be one of these two options. And we just need to determine if we know sigma, so it'll be a z-score test, or if we know the sample standard deviation S, and then it'll be a t-test. So let's read the problem and see which one they gave us. Let me get back to my problem if I can. Okay, so it says, based on a sample of 70 people, the sample mean GPA is 2.41 with a standard deviation of 0.03. So which standard deviation are we talking about here? Are we talking about sigma, the population standard deviation, or are we talking about S, the sample standard deviation? And the answer is we are talking about S, the sample standard deviation. How do I know that? Because it says based on a sample, and then it goes on to give us the stats, the statistics for that sample. The statistics are a sample size of 70, a sample mean of 2.41, and a sample standard deviation of 0.03. So when we're writing all of this out on our, gathering our information here, I always use green for sample statistics. So the sample stats are an N of 70, a sample mean, X bar, of 2.41, and a sample standard deviation of 0.03. All right, so now we have all the information we need from the problem, and we can start constructing our sketch here to represent our test. All right, we just determined that we are doing a t-test because we know S instead of sigma, and we have a right-tailed test with a significance level of 0.01. So let's draw critical region on the right. So our critical value is going to be a positive t-score, and it has an area of 0.01 to the right. So using that area, or actually using the left area, which is 1 minus alpha, right? So 0.99 on the left, we can use our t dot inverse on 0.99 with mean of 0, or not mean of 0 and standard deviation of 1. I forgot. We're not doing norm dot inverse. We're doing t dot inverse. Instead of a mean and a standard deviation, we gave it these degrees of freedom, which is always n minus 1. So since our n is 70, our degrees of freedom here is 69. All right, now that is your critical value. Okay, so we've set the goalpost. We know where our rejection region is. Now, just as a side note, if you had accidentally done t dot inverse on 0.01, you would have gotten the same answer but negative. This is why the sketch is so important. If you do your sketch and you know it's supposed to be on the right, to the right of 0 are positive numbers. So this couldn't be your answer. You should change it to a positive, okay? All right, so we're done with that. Now we're going to start focusing on the sample statistics. What we want to do is take our sample mean and turn it into a value that can be compared with the critical value. We need to convert this into a t-score. So how do we get t-scores? We take that sample mean, we subtract the 1 in the null hypothesis, that's your mu, and divide by the standard error. So that would be S divided by the square root of n, which is 70. So where am I getting that from? Well, I know it by heart now, but if I was looking at this formula, that's what I'm doing right here. This formula, t equals x bar minus mu divided by s divided by the square root of n. All right, so now that I know how I'm going to calculate this, let me go ahead and get my test statistic, which is a t-score in this case. My numerator is x bar 2.41 minus 2.4 from the null hypothesis divided by the standard deviation 0.03 over the square root of n, which is 70. Okay, so if you need to pause it and write that down, that's what it should look like. Okay, you should have all that. And then you should get this answer for your test statistic. So this is our green boundary. So we're going to now place it on the sketch and see if it falls in the red region. So the test statistic is 2.79 approximately, which is farther to the right than our critical value. So I'm going to put that over here, 2.79-ish. That's my test statistic. Okay, now the boundary I've already put on there. The area in the tail there is called the probability value, which we call p-val for short. It's the probability of getting a test statistic at least that extreme. So we're going to find an area now. Now, when you're finding an area, you would use distribution, right? And this is a t distribution. So you're going to use t dot dist. You're going to put in your boundary, which is your test statistic of 2.79. Now be careful though, because now when I put in my test statistic and then my degrees of freedom and true for cumulative, I see an answer that is way too large to possibly be a p-value that is this tiny little green shaded area here. The p-value is clearly tiny, right? Now remember, the entire area under the curve is 1. Half of the area under the curve is 0.5. So this tiny little green region here should be less than 0.5. And seeing an answer like this doesn't make sense. If you realize that, remember, the distribution functions always give you an area to the left. So that 0.996 is actually the area to the left of this boundary. If I want the area to the right of the boundary, I have to take this answer and subtract it from 1. And that's an answer that actually makes sense. Now, if you're getting confused about all of this, remember that I have these kind of cheat sheets for the different types of tests. And notice that here on this page where it says t-tests, under the right tail, I have the information about how you would find your critical value, t dot inverse on 1 minus alpha. Remember, that's what we did here. 1 minus alpha was 0.99. That's how we found our critical value, t dot inverse. And then the p-value is 1 minus t dot dis, right? But just be careful. Make sure you're paying attention. If you make a mistake, if you're doing your sketches and paying attention to making sure your critical value is positive if it's on the right, negative if it's on the left, right? You have to just have some awareness in case you make some kind of error, right? Because this thing is symmetric. Sometimes it's just the sign that matters. The p-value, remember, if it was greater than 0.5, something's wrong. Subtract it from 1. That makes much more sense, right? And you can see how here it says 1 minus t dot dis, and then your test statistic. Now, one thing I do want to make clear is that if your test statistic is positive, I had to make sure, what am I trying to say? I just confused myself. What was I trying to even say? If my test statistic is positive, yeah, that's why it had to be 1 minus. Now, the only area that there could be a little bit of confusion is if it's two-tailed, because I only put the case, your p-value has to be doubled if it's two-tailed. You have to picture two separate test statistics, and you have a left area and a right area that you add together to get your total p-value. Now, here's the thing that I was thinking of that could be a little area of confusion is if this test statistic is positive, you might have an issue. You're going to have an issue. You have to make sure you're getting a small area. And so it's safer if you use the negative version of your test statistic for doing this. So just a little caveat there. Again, if you're doing your sketches, hopefully this is starting to take form. And I'm going to go ahead and end this video here.